So after discussing non-Fourier heat conduction model, and that is specifically applicable in case of welding, heating processes, now we will try to discuss the stress analysis model, and that is associated with the ultra short pulse laser heating process. So we will see that in this case stress analysis model, how the stress analysis model is actually different from the conventional laser welding process. So in this case we know that two temperature and the hot electron blast model, that deformation behavior of the thin metallic film can be analyzed, and that is under short pulse laser heating process is basically analyze this thing, assuming this thermal analysis is from the two temperature and hot electron blast models. But in this case the actual equation will be getting the based on the nonlinear elastic equation of motion. So that actually predict the displacement field, and that is a function of the time considering the effects of the dynamic nature of the, or we can call that dynamic thermoelasticity and temperature gradient in metal lattice. So in this case if we look into this two temperature model and the hot blast electron blast model, in the literature we can find out that they have analyzed the dynamic thermoelasticity and temperature gradient. The analysis can be done, but of course in this case also the displacement field can be represented as a function of time. But if you look into even non-Fourier heat conduction model with single phase lag also, in this case assuming the strain field is a function of the one dimensional space and temperature, and then once we assuming the strain field, and from the strain field we can estimate the static equation and then static equilibrium equations, and from that point of view we can make the in the equation in the form of a displacement, and then we can analyze the displacement, and then after analyzing the getting the displacement field, or we can say the lattice displacement field, then we can predict the strain field, and from the strain field it is possible to predict the stress field. This is the usual procedure for the stress analysis model. But in this particular case, if we consider the high parabolic thermoelasticity model, in this case it is very much nonlinear, and the numerical solution is actually tedious in presence of the two different relaxation times in the heat conduction equation. So in that case, if we introduce this, if we solve this hyperbolic thermoelasticity model, if we follow this particular model, then equation becomes very tedious and it's complex, and maybe computational part may be an issue in this particular process, because we account the two relaxation times in the heat conduction equation. So we will try to find out the stress analysis model, but simply what we have learned in the simple elastic analysis or simple elastoplastic analysis, the similar kind of the analysis can also be applicable. But of course in this case, this application of the in ultra short pulse laser, application of the laser flux is so rapid that in these cases probably we can use only the thermoelastic model may be sufficient to explain the different distortion field, and that in these cases we have analyzed the simple thermoelastic model but with so many assumptions. Strain field is estimated from the displacement field that we have already seen when we have analyzed the what we can develop the stress analysis model, because in general in any stress analysis model, that first we take the input from the thermal analysis, or maybe if there is any concentrated or distributed load as a boundary condition. So from there we can find out the first we solve the displacement field, to solve for displacement field. So first we estimate the displacement field, from the displacement field we can estimate the strain field, and from the strain we can correlate with convert it in terms of the stress field. That is the usual process. But if we consider the thermoelasticity, the dynamic thermoelasticity model, in this case there is inertia effect. So that means dynamic force balance of the system is required to consider the effect of the inertia in this particular system, specifically to the ultra short pulse laser heating system or ultra short pulse laser welding system, and it is associated with the second order differential equation, and then we need to solve this second order differential equation, then we will be getting output as a displacement field. And definitely apart from that, thermal stress is associated with the thermal strain, and this thermal strain normally we assume the elastic strain, and then once we estimate the thermal strain from the thermal expansion coefficients and the Young's modulus, from there we can find out what is the value of the thermal stress, and then the solution of the dynamic system, if we consider a second order differential equation in the form of a displacement field, then if we solve this equation, differential equation, they will be getting the displacement field, but this dynamic equation may consume the huge computational time, specifically for the 3D system. Therefore, most of the problem associated with the ultra short pulse laser heating process is either they solve the analytically or semi analytical approaches, but numerical approaches or numerical solution of this kind of equation is very much computationally expensive. At the same time, dynamic system of the thermal shock behavior, if we consider the dynamic in this dynamic system, and if we consider thermal shock, because it is very rapid process, the application of the heat flux and development of this thing, some time relaxation is there. So, then it may induce the thermal shock, that at the same time, because there is a pulse heating is there, and when one material is subjected to the pulse heating, there is a continuous change in the temperature or variation of the temperature, and wide variation in temperature may induce some amount of the thermal shock behavior associated with this particular system. So, therefore, once we consider thermal shock behavior with the application of the ultra short, it is actually converted to the simple static system to dynamic system. But if it is possible to convert this thing, if we neglect the inertia part, and then if we simply represent this system as a static system, then we can we can simplify the modeling approach of the stress analysis associated with the ultra short pulse laser reading. So, therefore, in this particular discussion, we can look into the static analysis in the dual phase lag non-Fourier heat conduction model, and therefore, in this case not account much error by neglecting the displacement inertia effect. If we neglect the inertia effect, there may not be that much of error in calculating the displacement field. Anyway, we simplified the model in case of ultra short pulse laser heating model as a simple static system. Then we will see that we know as a simple static system, the equilibrium of equations can be represented like this, that what is the internal stress generation in the body, sigma ij, and then external forces, or in terms of the body forces that make the balance of the system equal to 0. We can see the rho bi represent the body forces, and sigma ij is the stress tensor, but in these cases we consider the symmetric stress tensor. Now, these are the system of equilibrium equation. Now, total strain, we estimate, you know, that there is either elastic model, thermoelastic model, or thermoelastoplastic model. It is necessary to estimate what is the total strain component, which component we have to consider in this case. Since we use only the thermoelastic model, therefore, we consider the elastic strain. If the total strain consists of the elastic strain plus the thermal strain, and thermal strain depend on the temperature variation, and thermal strain, the temperature variation, as well as the temperature thermal expansion coefficients of the particular material. So, once we if we consider both elastic strain and thermal strain, then total thermoelastic incremental strain can be represented d epsilon equal to d epsilon E elastic part, and the d epsilon Th. So, that is the thermal part, thermal strain component. Now, increment of the stress is simply d sigma equal to d is the this matrix associated with the all the material properties, and into d epsilon E, that means elastic component. That means we use the thermoelastic analysis. Therefore, the stress we relate the strain assuming the elastic component only. So, we are not considering the plasticity part in this particular process. Then elastic stiffness matrix d elastic, it should consist of the total strain minus of, this is the thermal stiffness matrix, and the temperature difference dt. So, this will induce the total incremental stress. So, therefore, total incremental stress can be represent the total strain minus the only the thermal strain component. So, if we find out in this are the relation, and we have observed in the simple stress analysis model or elastoplastic analysis model, it was necessary to incorporate the other plastic strain component also, but in these cases we are neglecting this plastic strain part. Now, if in a static system, if we follow the potential energy minimization problem, then we have already shown in the module 2, then during the stress analysis model, what is the potential energy minimization of a system and what we can reach this kind of equation, that equilibrium displacement. So, K is the stiffness metric and delta U is the incremental nodal displacement equal to dF. D is the incremental load vector. So, in this case, the incremental load vector, we can see the stiffness metric and incremental nodal displacement term equal to the incremental load vector. So, this the equation of the Ax equal to B in the matrix form. So, if we solve this particular matrix Ax equal to B, we will be getting the x value. That means, what is the incremental value? D U will be the output in this case. So, that means displacement field will be getting each and every node point. But remember, in this particular case, when you are looking into only the thermoelastic analysis, so in this case, maybe if we assume the strain is stress is proportional to the strain up to the yield point, so that it follow the linear curve. So, in this case, incremental can be very high, even incremental can be in single step incremental can be considered, because in this case the elastic within the up to the yield point, the stress versus strain follow the linear path. So, which is different from the plasticity model, because plasticity model, if you look into the elastoplastic, that means if we look into the simple stress strain curve of a universal tensile static specimen, in this case when it crosses the yield point, then it becomes the curve becomes non-linear. So, therefore, in that cases it is necessary to make the analysis for the by dividing the total small strain component, and we analyzing this and keep on updating the stress or strain value. But if path is linear, then large amount of the increment can be considered as a single step. So, that is the difference from the simple elastic analysis as compared to the elastoplastic analysis. Now, once we look into the equilibrium displacement in this case, but we need all this relation, that what we can correlate, we can relate between the strain and displacement. So, if we assume the small deformation theory, maybe rotational degrees of freedom, other component can be neglected, or maybe second order differentiation of the displacement field. If we neglect this part, then we can use this simple relation between the strain versus displacement. So, that has to be decided first, what is the relation between the strain and displacement. We will be using this particular equation. So, in the matrix form, it can be represented this thing, epsilon equal to B into B is the strain displacement matrix, that we have already explained in the stress analysis model. So, this is the relation between the stress, strain and the displacement field. Now, we solve for this equation, because finally we will be solving this equation. In this case, if we solve this equation, then we will be getting what is the value of the incremental or displacement value. So, once we get the displacement field, so we can estimate what is the value of the strain value. So, once we get the strain value, then from the strain value, so we can estimate the stress value. So, this way we can find out the what is the value of the, it means that first we are calculating the displacement from the matrix equation, we solve it for the displacement field, we will be getting the displacement field each and every node point, then we convert it to this displacement to the strain value. So, once we getting the strain value, then this strain can be converted to the stress value. So, that is why we will be getting the displacement field, strain field and the stress field for each and in a particular domain. And once we get the in incremental form also, current strain value and current displacement can be approximated, that can be updated with compared to the what is happening in the previous step, and then we will be getting this solution. But it is also sometimes necessary to estimate what is the value of the effective equilibrium or effective stress value. The effective stress value, which is a component of the three different stress component. In this case, if we assume the sigma 1, sigma 2, sigma 3, the three different components, then we can finding out the effective value in terms of the, it means that at any state we will be getting the three dimensional stress value. So, say in this case, maybe within the elastic limit, it can be say sigma x, sigma y and sigma z, because or this sigma x, sigma y and sigma z represent the principal stress values. Now, once you get the principal stress value, then the single value can be represented using this equation. So, it means that the three dimensional state of the stress can be represented on a single value, that is the equivalent stress value. So, we have done some analysis, that means validation of this model, stress analysis model, and what we have done some thermal analysis on the of a gold film, and that just with a similar material we can analyze the stress and strain field also as well. But in this case, we have considered the multi-layer That means there are two layers of the gold film, the layer 1 and layer 2, both are 50 nanometer thickness. So, that means total domain is the thickness of the domain will be the 100 nanometer gold film. So, in this case peak power of the ultra short pulse sensor is used. Peak power is 2.66 kilowatt and pulse duration is 0.1 picosecond is the pulse duration and 76 megahertz is the frequency. So, using these cases we have analyzed the stresses in this particular thin film of the gold. Now, in this case if you look into the domain, we have created this domain, the layer 1 and layer 2, but in between we have created one single layer of the contact elements. So, this contact elements takes care of only the thermal contact resistance between these two layers. So, we can validate we can do the similar heat transfer analysis what we have done using the non-Fourier heat conduction model. So, we can do the heat transfer analysis, then we will be getting the temperature distribution, and we can validate the model by the known experimental data also. So, we can validate this experimental data is available actually with the 100 nanometer thickness. So, if we assuming the no contact resistance, the continuous layer of the 100 nanometer gold film, and for that purposes we have done some thermal analysis using non-Fourier heat conduction, then we can find out that this is the temperature distribution, and we can see this is the normalized temperature we can find out, and then we compare with the experimental data. So, similar kind of the graph we have analyzed in this case also, that in this case contact layer is actually 1 nanometer, only the 1 nanometer the contact length, that means contact layer thickness 1 nanometer is used in this particular problem, and we have analyzed this thing what is the effect of the contact resistance. So, contact coefficients is actually varied from 10 to the 5 to 10 to the 15 kg per second cube per Kelvin, and assume the 0 once the material melts. So, once the material melts, so contact resistance becomes 0, but before melting we assume that these two different there is wide variability in the contact resistance, and we are getting this kind of the profile, temperature profile. So, with respect to time, so we can see that single layer and the two layer, single layer means single layer 100 nanometer and the two layers of the 50 nanometer with some contact resistance. So, at the center point and the 1 micrometer away from the center point, these two cases we can plot the time temperature profile. We can see there is a temperature difference is there. So, it is at the center point as well as the 1 micrometer away from the center point, these 2 points there is a temperature difference are there. At the same time that single layer and the two layer. So, therefore, two different thermal contact resistance we can find out that even if I use the thermal contact resistance there is a wide variation of thermal contact resistance, but temperature profile is almost similar. It means that we can optimize the contact coefficients in such a way that simulation is independent of the contact resistance value. So, that is why that we have shown that independent of the contact resistance. Then we can further analyze this temperature we accept this temperature distribution and further use this temperature profile for the analysis of the stress generation in this particular case. So, in this case the low resistance and the high resistance, this particular and the single layer and the two layer, there is a temperature profile are completely different, that is obvious in this case. But peak temperature reaches at 0.3 picosecond, although the pulse duration was 0.1 picosecond, and in this case no contact resistance, but in this case of with the contact resistance there is a delay to reach the peak temperature, that is 2.87 picosecond. So, that means if you use the contact resistance, that means there is a multi-layer film. In this case the thermal inertia effect is more active because it takes much more time to reach the peak temperature. See, we have done some simulation that for these cases the temperature profile we have tried to plot the temperature profile, and we can see that at 0.3 picosecond, that means at this point it reaches the maximum temperature, that means peak temperature of the system, and then gradually decreasing 0.5 picosecond, 1 picosecond the temperature profile we can observe 1.35 and then 1.4 picosecond. It means that maximum temperature is reached at 300 femtosecond or 0.3 picoseconds, although the pulse duration was only 100 femtosecond. So, it means that thermal inertia effect is active in this particular, that we have already discussed and when in non-Fourier heat conduction model also. but depth of the heat affected zone increases gradually during the cooling period of a pulse, particular pulse. If you look into the depth of the heat affected zone, if we consider, and that actually gradually increasing even depth during the cooling phase of a particular pulse. So, that is the typical characteristics of the ultra short pulse laser process. Now, we have analyzed the distortion displacement field first, and then we have plotted the displacement field and using some boundary constant. So, we put some boundary condition, restrict the boundary to particular deformation to restrict the deformation of the boundary. Then we have done simulation for single layer and double layer both, and double layer means 50 nanometer plus 50 nanometer and single layer 100 nanometer, these two cases with boundary constants. And then first pulse, with application of the first pulse, we can see the figure shows the single at the 0.3 picosecond what is the distortion field or displacement field. So, effective displacement may be magnitude of the at different time instance. So, magnitude of the vector. So, effective displacement, though then effective displacement means root over of u square plus v square plus w square, or the u v w represent the displacement along the x, y and z direction. So, the magnitude if you represents this first figure represents the effective displacement, the maximum magnitude is less than that of the 1 micrometer. We can observe that maximum magnitude is less than 1 micrometer. So, with the constant value, if it is the single layer and the third one is the double layer. In this case, that is 0.3 picosecond and 1 picosecond and 2.8 picosecond. So, in this case, deformation is confined locally around the heat affected zone. That is obvious, the deformation is actually confined mainly the heat affected zone, not distributed to other, and we can see there is no buckling kind of things are not there. But deformation concentrated on the edge without any buckling. So, at the edge without any buckling, it is concentrated at the edge, but displacement decreases gradually during the pulse off period. That means up to the 0.3 second it reaches the maximum point, then that displacement decreases gradually during the pulse off period, means the once pulse is off at that period there is a displacement field actually gradually decreases. So, overall displacement is very low in case of the double layer elements. So, you can see as compared to the single layer, the double layer element overall displacement field is very low. Because presence of the thermal contact resistance at the interface. That means the thermal contact resistance reduces the temperature difference, special temperature differences, because we estimate the thermal strength is the alpha delta T. So, the delta T is small in this particular cases when we are using any kind of the contact resistance or multi-layer film. So, similar kind of the analysis also done, but without any boundary constant. So, that means the thin layer or film is free to move. So, if you look into that at a single layer as well as the double layer and the similar time, we can see that no mechanical constant, magnitude of the displacement is reduced and drastically, it is almost 1/100th times less as compared to with the boundary constant. So, maximum magnitude is only 10 to 15 nanometer only, but all the surfaces except the thermally loaded area remain the traction free. If you look into only the displacement, we can observe only near about the thermal field, but thermally loaded area which remains the traction free, but only mechanism to generate the strain, because high temperature gradient where additive effect of the reaction forces due to the constants is not active. It means that since we are not applying any kind of the constant, so there is no kind of the additive forces available in these cases, and that is why it is free to move. So, it creates very less magnitude of the displacement field. There is buckling also, we can observe in the similar this field. If you see this part, it shows there is some small amount of the buckling is there when geometry is free from any mechanical constant. That means if there is a mechanical constant, we observe there is no buckling, but it is free from mechanical constant, we can observe some buckling is there, but not much change in the magnitude. Magnitude not much changes in presence of the thermal contact resistance. We can see the presence of the thermal contact resistance does not change the magnitude much, but ratio of the maximum displacement distortion to the thickness of the film. When you compare what is the maximum displacement field in this particular cases, the ratio of the maximum displacement field with the thickness is very high as compared to the conventional heating and the cooling process. So, in this particular the thin film, they may at the localized position, it may the ratio can be very high. That means it means that what is the maximum value of the displacement field, that is very much high as compared to the thickness of the particular layer. Similarly, stress field also with the boundary constant, we can plot the stress field. We can observe the different both the single layer as well as the double layer. We can find out that equivalent thermal stress are represented in this case, the distribution of that also. Equivalent thermal stress means the 3-dimensional stress we converting in the representing in some on the single value of the stress. So therefore, stress field is also confined in the very small zone, and due to the application of the mechanical boundary condition, we can see the it is confined to the very small zone, and the maximum stress value is 0.3 gigapascal, and which is comparable with as compared to the yield stress value of the gold, because yield stress value of the gold is 120 megapascal. So in that case, the maximum stress value 0.3 gigapascal is comparable with respect to yield stress. It means that plastic deformation may occur due to the thermal strain, but we have not analyzed the plasticity in this particular cases. So there may be the brittle fracture due to this thermal shock load, because in this particular case the application of the load is there is a temperature variation is there, because this is a pulse. We can see that during off pulse there is a decrement of this cool down the temperature from the maximum temperature. Therefore, this kind of nature of the temperature can induce some amount of the thermal shock load. So therefore, the maximum stress value is relaxed during the cooling phase of the single pulse because of the presence of the thermal shock, and that thermal shock can induce may induce the brittle fracture. But thermal stress is less when the metal is subjected to the contact resistance. So we can see when thermal stress is less, if you see as compared to the other cases, that means single layer, then due to the contact resistance, thermal stress value is actually less in this particular case. Similar analysis we can do equivalent thermal stress, but without any boundary constant. But if you look into don't put any kind of the boundary constant, the magnitude of the thermal stress is mainly confined to the zone of the heat affected zone in this case. So, but magnitude of the thermal stress is reduced drastically as compared to with the constant. But surface metal is free, at the surface the metal is free to expand and produce less mechanical constant, because in this case the surface is free. So there is no constant, it is free to expand. That is why the generation of the stress in this particular cases, thermal stress is very less. That almost stress distribution is equivalent to the thermal temperature distribution. Basically which zone there is a temperature distribution, at the same zone we can see the distribution of the stresses, although magnitude is very less in this particular case. Therefore, temperature distribution is the main inhibiting factor to produce the thermal strain or strains without any mechanical constant. It means that since we are not applying any kind of the mechanical constant, then temperature distribution is mainly the temperature difference is mainly the responsible to induce the thermal strain in this particular case. But when we put the boundary constant, the constant can induce some amount of the strain value also. So therefore, the distortion the stress distribution is mainly governed by the mechanical boundary condition in such a small geometry. It means that it is very important to precisely define the boundary constant, because the maximum amount of the strain or stress can be generated because of the boundary constants. But if there is no boundary constant, then magnitude of the stress or strain is very less. It means that in the thin film structure, it is very important the boundary constant is actually induce the maximum amount of the strain or stress as compared to the only thermal stress or thermal strain. In summary, we can say associated with the non-Fourier heat conduction model and as well as the stress analysis model, we can see the both thermal and the coupled thermomechanical model using the elastic analysis is performed, or maybe in these cases we have explained in the light of by using the ultra short pulse laser heating process. So 3D finite element based model is possible to develop using the non-Fourier heat conduction model, and we have shown that dual phase lock model can be possible to develop. But from the temperature distribution, it is obvious that when it is any component, even it is a very thin component subjected to the ultra short pulse laser, then it is basically associated some kind of the thermal shock loading. So thermal shock loading, it may create the thermal fatigue in the structure. So that studies different aspects. Therefore, significant effect is observed in the temperature distribution due to the consideration of the thermal contact resistance. We have seen that if we consider thermal contact resistance in the multi-layer field, the temperature distribution, there is a variation of the temperature distribution. Distortion as well as the stress field is influenced mainly by the mechanical constant that we can observe also. Only the thermal strain can induce not that much of the stress as value. The stress and distortion for the constant model are greater in magnitude as compared to the unconstant condition. That is obvious, because when you put the some constant in the boundary constant, the magnitude of the distortion and the strain or strain field is much more as compared to the without any boundary constant. Therefore, associated thermal fatigue behavior of the cyclic loading, in this case the cyclic loading means the temperature variation that follow some kind of a or cyclic loading or follow kind of pattern, and for the different conditions are necessary to reliably establish the process model reported in this particular module. So far we have discussed. It means that it is also necessary to consider the thermal fatigue, or that can be another direction of the study associated with the non-Fourier heat conduction. So thank you very much for your kind attention, and here this is the end of the module 8 of this particular course, finite element modeling of the welding process. Next time we will start in the last module, that is the module 8, which is associated with the additive manufacturing process. So thank you very much.